Hey everyone, this is Mr. Ferentz. We are going to continue looking at one-dimensional motion, and today we're going to look at a topic called kinematics, which is a way of describing motion using math and equations that can be a little simpler than using graphs. Little bit of vocabulary. Make sure you feel comfortable talking about these words and what they mean and how they're used, because they have very specific meanings in physics. When we talk about this linear motion or one-dimensional motion, really we're just looking at going in a line. So either we're going to the right or to the left. Either we're going up or down. Either we're going forward or back. And we have these different quantities, these amounts, these measurements that we have to pay attention to. The first is called time. Obviously, this is how long something is in motion for. In science, in this class, most of the time we measure this in seconds, but we can measure it in different units like hours, years, centuries, whatever. So that's why we've been working on unit conversion, so we can jump back and forth between these units. We will also pay attention to something called distance. This is how far something travels in its path. Like I said, in science, we generally measure this in meters or centimeters or kilometers. We could also use other units of measurement. And we measure these distances and we measure lengths of objects using a ruler or a meter stick or a tape measure. In our everyday lives as Americans, we are used to using what is called the English system or the imperial system, measuring things in feet and inches and yards. In science, we use a different system of measurement. That's because every scientist in the world has agreed that this is the system we're going to use, so we can share our measurements and our observations with each other. So we measure everything in meters, and we can look at centimeters, millimeters, kilometers, kilometers, but our base unit of measurement is going to be the meter. And as you go through this course, it will be helpful to just sort of get used to thinking about how big a meter is, because it'll make it easier for you to visualize. These are units of measurement and how to convert back and forth between them. You won't have to memorize any of these, but these first three, going from meters, kilometers or kilometers, millimeters, and centimeters, we are going to be using those a lot. So you will probably end up memorizing them just because we're using them so much. The other ones, not as much, but again, they're just for our reference. Okay, so with these vocabulary terms, we're going to look at how speed and velocity and acceleration are related. Speed and velocity are not always the same thing. They're mostly the same thing, but there's a little bit of difference between them. The biggest difference is that velocity has this component of the direction that you're going in, as well as just how fast you're going. And we'll talk more about what these mean and how to figure them out. Speed is simply how fast you're going. This is the distance that you travel divided by the amount of time it takes you to get there. And that's it. So as a very quick example, a swimmer is swimming a lap in a pool that is 50 meters long. Okay, so the distance that she travels is not actually 50 meters. The distance she's traveling, because she's swimming an entire lap, the distance she's traveling, and for distance we usually use the variable x, is 100 meters, because it's a lap. She's going all the way down and all the way back. The time that it takes her to travel this, takes her 20 seconds to get down there. It takes her 25 seconds to come back. So the time, and we use the variable t, I put a little curve on it just so I know that it's not a plus, is 45 seconds. So her speed is going to be distance divided by time. So 100 meters divided by 45 seconds, and that's 2.2, hey, check it out, meters per second. So that is the unit of speed and also of velocity. So that is her average speed for this lap. Pretty straightforward. Um, as we talk about the difference between speed and velocity, all of the units of measurement that we use in physics are either a scalar or this other thing called a vector, which we'll talk about in a minute. Scalars have a magnitude, so they have a number associated with them and a unit of measurement, but they don't have a direction. Okay, so how tall are you? 6'1". It's not like, oh, 6'1" north, 6'1" that way. It's just 6'1". So these just have a number. But these vectors have this number, have this magnitude, but also a direction. And we can talk about the direction in terms of compass directions, okay, so going east or going north. With these equations, we can also talk about the directions using positive or negative numbers, or positive or negative signs, rather. So, you're traveling this way in the positive direction. So my velocity is positive 10 meters per second, or my velocity is negative 10 meters per second because I'm traveling at the same speed, but in the other direction. So displacement is related to distance, but it has to do with not just how far you've gone, but where you are compared to where you started. Okay, so it can be the distance you've traveled, but it has to do with, it has to be compared to your starting point. So if you run around one lap around a track, the distance that you've traveled is 1/4 mile. But if you are talking about your displacement, if you go all the way around a track and come back exactly to where you started, your displacement is actually 0 because you're right where you started. So this direction is really, really, really important. So just keep that in mind. When we're looking at, for the first week or two of this unit, we're going to look at stuff that's just moving in one direction or one dimension. So if something's moving horizontally, it's easy for me to visualize this if I think of moving along a number line. Okay, so we're either going to the positive direction or the negative direction. Generally, the right is positive, left is negative, but not always. If you want to flip it around, go for it. Same thing with vertical displacement. So if something is moving up or down, I think of it as a number line, just standing on end. Generally, up is positive, down is negative. Doesn't always have to be. If you want to switch that around, knock yourself out. So when we're looking at average velocity, we talked about how speed is distance divided by time. Velocity is displacement divided by time. Okay, so that is defined as the change in your position divided by the change in your time. Now, these triangles are the Greek letter delta, and in science, they are used to represent change. So we just talk about this is the change in x, the change in t. And we can rewrite those instead of saying just delta x. This is your final position minus your initial position. That's what these subscripts mean. This is your final time minus your initial time, which is often just 0. So we can use this equation the same way we were talking about speed to figure out what your average velocity is. Acceleration, on the other hand, tells us not about our change in position or our change in displacement, but it tells us about our change in velocity. So here's a data table where we have a car that's accelerating from rest. Okay, so it's starting from a stop. And as you can see, every second, its velocity is changing. It's getting faster and faster and faster. That's acceleration. So the acceleration of this car, if you take a look at this, okay, so it goes over 1 second, it gets 10 meters per second faster. Over the next second, it gets 10 meters per second faster. Over the next 10 meters per second. So the acceleration, we would actually call this 10 meters per second, if that makes sense. So what I'm saying is every second that passes, we're getting 10 meters per second faster. Our velocity is increasing by 10 meters per second every single second that we're going. It sounds kind of confusing when you say 10 meters per second per second. So most of the time we'll say 10 meters per second squared. And we'll write it like this, m/s squared. That is the unit of measurement for acceleration. Be very, very careful, because that does not mean that the number itself is getting squared. That is a common mistake. This is just a weird unit of measurement. It doesn't mean we're doing anything with the number. So I would just say here that the acceleration is 10 meters per second squared. That's it. But making a table like that isn't really simple. So it's a lot easier to do this using an equation. This equation looks very similar to our equation for velocity, right? And so our acceleration is the change in our velocity divided by the change in time, or just the difference between our final and our initial. Now, this is a good equation to use if we have our two different velocities and we know how much time we were accelerating for. But often we may not be given some of this information. We may be trying to find out, instead of trying to figure out what the acceleration is, we might be trying to figure out what our final velocity is. We may know the acceleration and we want to figure out, okay, if we speed up, what's our final speed going to be, or our final velocity going to be? So this equation that we just had on this previous slide, we can rearrange this to solve for VF. And we will end up getting this equation right here. The T final and T initial, that sort of disappears because most of the time our initial time is just going to be 0. So we're really just looking at this final time. So that's why I'm just writing T, just to simplify it. So this equation is a really good way for us to look at how fast we started, how fast we end up going, how much we're accelerating, how much time we're accelerating for. This equation is one of what we call the kinematics equations. There are 4 of them, and they are going to be your new best friend for about the next month. These are the equations. You want to write these down, highlight them, draw a box around them, put them on an index card. These equations are going to be used every single day. And so you want to make sure they're somewhere where you can refer to them over and over and over and over again. They really just relate our different velocities, our acceleration, our time, and our different positions. Over here on the right, I have, for your benefit, just sort of given you a variable that doesn't show up in the equation. So like this top equation right here, x, our distance or our displacement, doesn't show up in this equation at all. This is to sort of help you figure out which equation to use as we get into the habit of solving physics problems. So we'll practice these problems. When we meet, we'll do some example stuff. You'll work on some on your own. But make sure you have these equations written down. Make sure you're paying close attention to them. Like I said, they are going to be very, very valuable, and you will get to know them very, very well. So in the meantime, take care of yourself. Let me know if you have any questions, and I will talk to you soon.